Everybody. Today in this session we are going to discuss regarding the coagulation and flocculation. As you know that the water received at the water treatment plant after aeration process, it can be brought to the coagulation unit, and where the particles are settled by giving the initial chemical action. Thereafter some particles are again left after the coagulation process, and those are removed by using the flocculation process. So what these processes are there, and what is the theory behind this, that we are going to learn today. So if you see the why coagulation and the flocculation is necessary, it's because of the particle size and their settling property, you can say. Okay, so particle diameter is mentioned here in this table. You can see 10 mm, which is a type of pebble, and which settles with the velocity 0.73 meter per second. So it will settle fastly. So 1 mm size particle, it is a coarse sand, it settles with 0.23 meter per second. Okay, it is by gravity settling. Then zero point 0.1 mm size particle, it settles down, which is a fine sand, 0.6 meter per minute. Then 0.01 mm size, it is a silt, 8.6 uh, meter per day. But if you see, if a 10 micron particle, it is a large colloid, it is called as a zero point 0.3 meter per year. And 1 nano particle, which is a small colloid, you can understand here, 3 meter per million year. So it is not possible to settle all the particles only by the sedimentation process or a natural sedimentation processes or a gravity settling. So we'll have to apply some chemical action here to settle those particles. Now these colloids, which impart color and turbidity to the water, and which is aesthetically not acceptable. That's why this treatment is necessary. And colloids are the particles are so small, by gravity settling it is not possible. So this we'll have to remember why the coagulation and the flocculation is necessary in the water treatment. So this colloids, if you see a Tyndall effect, if you see ability of a colloid to scatter the light. So if you pass a beam of light through a water container which is a transparent, so you can see the various colloidal particles there. Okay, so this is called as the Tyndall effect. Please remember this. Then what are the characteristics? Solids disperse in the liquid, which will not settle by the force of gravity when solid colloid stays in the suspension and does not settle in the system, is in a stable condition. Large specific area, large surface area per unit volume of a particles. It makes colloids can absorb materials such as water molecular and ions, and it opposes electrostatic comparing to the water. Now regarding the colloids, remember there are hydrophilic and hydrophobic colloids. Now concentrate on these two words. The water living colloids are called as a hydrophilic. At the water heating contrary, water heating colloids are called as a hydrophobic colloids. Okay, so molecules arrange themselves so that hydrophobic portions are oriented towards each other. So that's why the it's possible to get settling. If a large hydrophobic macromolecule, giant molecule it is called as, needs to exist in water in a shield, hydrophobic molecules embed themselves into the macromolecule, leaving the hydrophilic ends to interact with water. So this hydrophilic and hydrophobic nature of the colloids, that is responsible for the coagulation process or the settling action of the particles, and that depends upon the interparticle attraction. So this figure you can see, okay, where the colloids are described as the hydrophilic and hydrophobic colloids. So if you see hydrophilic colloids, in these molecules, the hydrophilic parts are on the surface end, and the hydrophobic parts are folded in into make a hydrophilic colloid. Now hydrophilic parts become attached to the water and partially hydrated. Okay, So here if you see a hydrophobic particle has been shown where the repulsion is there because of the same nature of the um, charge which is available on these particles. So you can observe here adsorbed anions can interact with the water, and water contains all the cations and anions present in this. So these two characteristics, hydrophilic and hydrophobic, that we'll have to remember. Now, what is actually hydrophilic colloid and hydrophobic colloid? Colloidal, in case of hydrophilic colloids, colloidal solid surface has water soluble group such as amino, carboxyl, sulfonic, hydroxyl. Here we have to little bit we have to concentrate on the chemistry. What are these groups are there? These water soluble groups can promote water of hydration of colloidal particles, right? Hydrophilic colloids are general organic colloids such as proteins and their degradation products. Then hydrophobic colloids. In the hydrophobic, there is no obvious water of hydration of the colloidal particles, and hydrophilic colloids are general inorganic colloids such as clay. And the colloidal stability, if you see in the water, okay, as the repulsion is there between the two colloidal particles, the colloids have a net negative surface charge. Electrostatic force prevents them to from the agglomeration to come together because of this same charge. They cannot come together. Now again, Brownian motion keep these colloids in suspension. Because of this motion, they keep suspended in the um, liquid, and here in the case of the water is there. Impossible to remove colloids by the gravity settling. So that's why, because of this motion and these forces, it is impossible to remove these colloids only by the gravity settling. That's why it is necessary to introduce the chemicals there, so that the possible settling of these particles may be achieved, right? Now again, the electrostatic force is also playing the role there. Yeah, the ionization of the this surface groups, the adsorption of the ions from surrounding solution, and the ion deficit within the mineral lattice for the colloidal minerals. So all these factors which are associated with the electrostatic force, that will also consider in the theory of this coagulation. Okay, if you see this, the stability of the colloidal particles in the water is dependent on the electrostatic force and the van der Waals forces. Now, electrostatic force and the van der Waals forces can be represented by the zeta potential, and that zeta potential is given by this formula. This symbol stands for the zeta, 4 pi q d divided by this capital D, where q is the charge per unit area, small d is the thickness of the layer surrounding the shear surface through which the charge is effective, and capital D is the dielectric constant of the liquid. Now if you concentrate on this particular figure, here on the repulsive forces are there, on this side the attractive forces are there, and this particular line indicates the distance between the cell and surface, right? So this line indicates the electric static force, and this particular line, blue line, indicates the van der Waals forces, which is a irreversible adhesion, and this line indicates the initial reversible adhesion there. Okay, so here especially this zeta potential is the scientific term for the electrokinetic potential in the colloidal dispersion. In colloidal chemistry literature, it is usually denoted by the Greek letter zeta, and hence zeta potential, and usual units volts or the millivolts. Okay, when we are calculating that. So this we have to remember how the repulsive forces and attractive forces. The repulsive forces are associated with this electrostatic force, right? And attractive force you can see here, the which are associated with the van der Waals forces. Now colloidal destabilization. So in that again these parameters are important. By change charge neutralization, colloids can be destabilized. This is a very important statement here. Then positively charged ions, for example Na plus, Mg2, Al3, Fe3, etc., neutralize the colloidal negative charges and thus destabilize them. With destabilization, colloids aggregate in size and start to status. Because of this, the colloidal particles come together and they start settling down. Now, what is the theory of this? The reducing the zeta potential to van der Waals force level when coagulant adding to the water, it will hydrolysis this form positively charged hydroxymetallic ion complex. This positive charges hydroxy metallic with absorbed on the negative charge of the colloid surface to reduce the zeta potential to destabilization point. These destabilized colloids and hydroxy metallic complex by the van der Waals forces absorption and flocculation. These processes can be spreaded by the agitation. So when you add the chemicals in this, so we have to agitate the water so that the this settling action that will accelerate. Now the here the important 2 points are there: particle bridging and the this enmeshment of the particles. Now, coagulant complex can be polymerized as the concentration is larger than the KSP, it will settle down. Now, what is coagulation? Again, the coagulation is the destabilization of the colloids by addition of the chemicals that neutralizes the negative charges. The chemicals are known as a coagulants, usually higher valence cationic salt as Al3, Fe3, etc. Coagulation is essentially a chemical process. Now you can see this rapid mixing is necessary there. So it is required to disperse the coagulant throughout the liquid so that this adhesion between the particle takes place and the particle settle down. Now coagulation has three forms: as a electrokinetic, which is zeta potential reduction; perikinetic, Brownian movement to make interparticle contact; and orthokinetic, agitation to make the interparticle contact. So these three processes are or coagulation forms are important in the coagulation theory. Now there are various types of coagulants are there, as aluminum sulfate, ferrous sulfate, ferric sulfate, ferric chloride, then polyaluminum chloride, lime, etc. These are added. These are the chemical formulas of those. And coagulant aids to produce a quick forming, dense, rapid settling floc, and to ensure optimum coagulation. Three types of kinds of coagulant aids are used: as the alkalinity addition, which is CaO, CaOH2 and Na2CO3, and polyelectrolytes, which are anionic negative charges, cationic cationic this positive charge, then polyampholytes, which are having the both negative and positive charges, right? So here what type of coagulants are to be used and how the coagulant aids are working, that is very important to remember. Now again next process there. So in instead only by addition of the coagulants and by giving the agitation only, the all the particles are not settling. Still there are some particles which are present in the water which are not settled. Now what to do about this? Now flocculation is the next process, which is the agglomeration of the destabilized particles into a large size particles known as flocks. This word flocks is very important here, which can be effectively removed by sedimentation and flotation. The addition of another reagent called as a flocculant, and a flocculant aid may promote the formation of flock. Okay, so here we are again very, this flocculant is very important word, okay, which is promoting the formation of the flocks, bringing the particles which are not possible in the coagulation process. These particles are brought together. Thus flocculation is essentially a physical process that describes the transport of destabilized particles. Now again, before deciding the coagulant dose, there is a one laboratory test which is available, which is called as a jar test. So in that initially we can find out the optimum dose of the optimum pH, and then we can find out the optimum dose of the coagulant. Now this jar test a laboratory procedure to determine the optimum pH and optimum coagulant dose. A jar test simulates the coagulation and flocculation processes. So it consists of the like these six jars are there which are provided with the stirrer. Six stirrers are there. Now fill the jars with the raw water sample, generally 500 or 1000 ml. Usually six jars are there. Adjust the pH of the jars while mixing the using by H2SO4 or NaOH or lime. pH is 5, 5.5, 6, 6.5, 7, 7.5. Likewise, it is adjusted. Add same dose of the selected coagulant. Now we have to select the coagulant either alum or iron to each jar, and coagulant dose 5 or 10 mg per liter, right, which is added. Then rapid mixing by using the stirrer. You can see it is provided with a stirrer there. These six jar you can observe, and rapid mix each jar at 100 to 150 rpm for 1 minute. The rapid mix helps to disperse the coagulant throughout each container, reduce the stirring speed to 25 to 30 rpm, and continue mixing for the 15 to 20 minutes. This slower mixing speed helps promote the flock formation and enhancing the particle collision, which leads to a larger flock. Turn off the mixer and allow the flocks to settle for 30 to 45 minutes. Then measure the final residual turbidity in each jar and plot the residual turbidity against pH. Okay, so you can see the settled particles are there. Now the pH of this lowest residual turbidity will be optimum pH. So if you plot the graph against the turbidity remaining, okay, and the pH, then this will be the optimum. You can say the pH, okay, residual turbidity versus the pH. This graph is plotted, and optimum pH here. In this case, it is 6.3, which is for example we have taken. Now we can find out the optimum coagulant dose. Now again what we'll have to do, repeat all the previous steps. Okay, and now this particular process again indicates the determination of the optimum coagulant dose, right? Now this time adjust the pH of all jars at the optimum, that is 6.3 found from the first test, right? Now while mixing the using the H2SO4 or the NaOH or lime, add different doses of the selected coagulant, iron, alum or iron to each jar. Coagulant dose that may be 5, 7, 10, 12, 15, 20 mg per liter. Rapid mix each jar at 100 or 150 rpm for 1 minute. The rapid mix helps dissolve the coagulant throughout each container. Reduce the stirring speed to 25 to 30 rpm and continue mixing for 15 to 20 minutes. Then this will be slowed down in the mixing speed, help to promote the flock formation by enhancing particle collision, which leads to the larger flocks, making the larger flocks. Turn off the mixers and allow the flocks to settle for 30 to 45 minutes. Then measure the final residual turbidity in each jar. Plot the turbidity against the coagulant dose. Now here you can see the coagulant dose and the turbidity remaining. Now from this particular graph we can find out the optimum coagulant dose which is to be given in for that water, right? So jar test which helps to find out the coagulant dose with the lowest residual turbidity will be the optimum coagulant dose. Now this rapid mixing, how it can achieved, and what is the objective of that? So to uniformly mix the coagulant with the colloidal matters present in the raw water so as to bring about colloidal destabilization. Then how to achieve the rapid mixing? Now there are two processes, like the horizontal flow and the vertical flow. You can see this, the baffles of the horizontal baffles are placed, and this is the movement of the water which takes place here, and these are the vertical baffles are there, so the water will move like this. Okay, so in the horizontal vapor tank the water flows in a horizontal direction, and the baffle walls helps to create turbulence when the water hit the surface and thus facilitating the mixing, right? And in the vertical baffle wall, the water flows in the vertical direction and the baffle walls help to create a turbulence which when the water hit the surface and thus facilitating the mixing. Okay, so here because of this turbulence created either vertical or horizontal movement, so target is achieved. Now again in this again we have to consider the few points where the hydraulic jump may arrive there, and that will help in the mixing of the water. Also in that inline flash mixing can be also used. You can see the coagulant added and the devices can be used for the inline flash mixing. And either you can go for the, if the mechanical mixing you are using, then back mix impeller can be used. You can see here the coagulant is added there and this mixing is carried out here. And either you can go for the flat blade impeller directly. So these are the blades which are here and the chemical feeding is there from the bottom, and this mixing is takes place. Now the flocculator design parameters are there. What design parameters are we have to consider? Now this is a slow and gentle mixing process. Flocculator is designed mainly to provide enough interparticle contacts to achieve particles agglomeration so that they can be effectively removed by sedimentation or flotation. Okay, so initially in this figure you can see these are moving because of the Brownian movement or this action, they are independently moving. But what is our target? To bring them together and make the flock and settle down those. Now the transport mechanism in that two points are important. Brownian motion for relatively small particles which follow random motion and collides with the other particles, which is a perikinetic motion as we have studied earlier. Differential settling, particles with different settling velocities in the vertical alignment collides when one overtakes the other, so which is a orthokinetic motion. Now you can see here the plan and elevation of this flocculator. The mechanical mixing using the different types of mechanical mixers promote the particle contact and thus their agglomeration, or which is a orthokinetic motion is there. So the water is moving there. These paddles are provided here. So we'll have to design this length, height, and also number of paddles. Now you can see in the plan, you can see the paddles are like this, and these are called as the transverse paddles, which are uh, giving the stirring action to the water. Okay, this is the isometric view of these paddles. Okay, the paddles can be designed like this so that the agglomeration of the particles can be achieved. Now the mixing and power calculation. So degree of the mixing is measured by the velocity gradient, which is G. Please remember all this terminology. Velocity gradient G. Then higher this velocity gradient G value, the intense the mixing and the vice versa, right? Now the velocity gradient is the relative velocity of two fluid particles at the given distance. Okay, when you are mixing, this velocity gradient is between the two particles, right? And that G is given as a dV by dy. So in this case it is 1 divided by zero point 0.1, as the example it is given, it is a tear per second, right? You can see this distance is given here. This is the velocity for the calculation of velocity distance. Two particles are there which are having the distance 0.1 meter, and you can see this is the velocity 1 meter per second. In mixer design, the following equation is more useful. You can see this equation is given as G is equal to, in bracket, P divided by V into pi raised to half, where the G is the velocity gradient which is per second, and P is the power input in watt, V is the tank volume in meter cube, and mu is the dynamic viscosity Pascal per second, Pascal second, sorry. G is the value for coagulation, which is one example is given here, 700 to 1000 per second, 3000 to 5000 per second for a mixing time, which is 30 to 60 seconds, and inline blender 1 to 2 second. So again, G value for the flocculation you can see 20 to 80 per second, and mixing time is 20 to 60 minutes, right? So in the flocculator design, GT, also known as the camp number, a product of G and T is commonly used as a design parameter. Please remember this product as a G and T, right? So typical GT for a flocculation is generally 2 into 10 raised to 4 to 10 raised to 5. So for large G velocity gradient and this T, right, gives the small dense flocks, and instead of vice versa you can say small G is there and large T, that will give the big but the light flocks, right? So you can see this variation, okay, in the this G value. So we need a big as well as dense flocks, which can be obtained by designing the flocculator with the different G values. So that's why, so this flocculation can be designed with the different G values by giving these rotations. Now just example for a power calculation have been shown here. Uh, how many horsepower can do we need to supply a flocculation basin to provide G value of 100 per second and GT that just we have seen away 1 lakh for a 10 mgd flow. Okay, so given mu is the this viscosity 0.89 into 10 raised to 3 Pascal second, and 1 HP is given as a 1745.7 watts. So by using the same formula, that retention time, that T is equal to GT divided by G, which is this uh, 1 lakh divided by 100, which is equal to 1000 seconds are there. Volume of flocculation basin, that V is equal to this 0.438 meter cube per second multiplied by the 1000 second. So which is we are calculating there as it is a 438 meter cube, 438 meter cube. Now the formulation again using that same formula, that G is equal to P divided by V into pi, which is raised to half. So putting the values here, the power can be calculated as a 5.22 HP. So this is the one of the example. So in the again coming lectures we are going to see such examples. But in the coagulation theory, remember where this GT coagulation and the flocculation theory, remember this velocity gradient and this T factor, time factor, plays a very important role in the settling down the particles. So here with this today we'll conclude, but in the coming lectures again we'll focus on the various parts of the units, water treatment units, and the related design theory. Thank you very much for joining the session.